Okay, so let's unpack this a bit. Imagine taking one of those tiny microcontrollers, right? The
Yeah.
affordable ones you might, tinker with on a weekend, and then turning that into the actual brain controlling some like complex industrial machine. That's pretty much what we're diving into today. Our mission really is to cut through the jargon, show you how the humble ESP32 gets turned into a proper powerhouse, a programmable logic controller, a PLC, and it's using this really powerful open source framework, Eclipse 4diac. We're going to dig into some surprising facts, some real world examples, basically give you a shortcut to understanding this fascinating blend of consumer tech and industrial automation. And all this thinking comes straight from the Project Logic US presentation, from DevCon 23. My friend Singer.
Yeah. And what's really striking there, I think, is how it bridges these two worlds that seem so far apart. You've got the ESP32, super accessible, everyone knows, right? And then you have industrial control, which is usually this very robust, closed-off kind of domain.
Totally different vibes.
Exactly. And this project just brings them together. It feels like it's really democratizing things.
Okay, so let's kick things off with the basics, just for anyone maybe less familiar. What is a PLC, fundamentally, and why are they, so important in automation?
Right. So at its heart, a PLC is basically a small, dedicated computer. Its job is managing technical processes. Think of it like the central coordinator. Doesn't matter if you're making a physical thing like a car on an assembly line or managing something less tangible like keeping a house perfectly heated. The PLC reads input signals from sensors, switches, stuff like that. It processes that information based on the program it's running. And then it controls outputs, actuators, motors, valves, lights to make things happen. Traditionally, you program them, you monitor them using a PC. And more these days, they're getting connected up to higher-level IoT systems for more data, more control.
Got it. So, okay, the motivation seems really clear then. Put that industrial brain onto the ESP32, which is everywhere and cheap. But what was the main roadblock, making that jump from a hobby chip to something running industrial gear? Was it just finding the right hardware?
You might think so, yeah. And it's true, there are actually quite a few ESP32 boards out there marketed as PLCs,
Yeah.
in boxes and things.
Okay.
So the hardware wasn't really the bottleneck. The real hurdle, the tricky part, was the software. Most of those existing ESP32 solutions, they're programmed in C++A, maybe using the Arduino IDE, and that just lacks what the industrial world expects, which is a real function block-like programming environment.
Okay.
That visual standardized way of building control logic. That was the missing piece.
Right, function blocks, that visual programming style. Okay, so the software hunt was on. What were some of the maybe surprising challenges or dead ends they hit looking at other PLC environments for the ESP32?
Well, they definitely explored the big names. For instance, Codis ES, very common in industry.
Yeah.
But nope, not available for the ESP32 directly. It needs a minimum, like a full Linux system or a Raspberry Pi. So that was out.
Okay.
Then there was Logi.CAD. Now, that could potentially run because there's a FreeOS version, which the ESP32 uses, but porting it properly, that looked really costly. A huge development effort. Even with the FreeOS base, it's not just plug and play.
Right, significant work involved.
Yeah. And finally, they checked out the OpenPLC project. You see that one mentioned online quite a bit. But it had some issues. It was, well, pretty old, running on Python 2, not Python 3.
Oh, wow.
Yeah, which caused installation headaches on Linux. And maybe most importantly, it was missing key features like monitor and watch capabilities. Those are absolutely essential for seeing what the PLC is doing in real time for debugging.
Okay, so OpenPLC had some real limitations. Given those experiences with CodisYS, Logi.CAD, and OpenPLC, what made them feel confident about Eclipse 4diac? Even if the ESP32 port was, as you said, pretty basic to start with, why wasn't it just another potential dead end?
That's a good question. I think two things really stood out. First, it's open source. That's a massive plus. Less vendor lock-in, more community potential. But the crucial factor was that someone had already done an initial ESP32 port. It wasn't perfect, it was basic, sure, but it worked. It was running. That gave them a concrete starting point. They weren't facing a complete unknown, They had something to build on.
That makes a huge difference. Okay, so 4diac becomes the foundation. What were the practical things they decided had to be possible for this to work as a real PLC on the ESP32 for their project Logi US?
Right.
What were the must-haves?
Right. They laid out some clear requirements. First off, you need to be able to flash the runtime onto the ESP32 just once. Like any normal ESP-ADF project, compile it, flash it over serial.
Okay, standard setup.
But after that, all the control logic, the actual PLC program, that needed to be transferable remotely. over Ethernet or Wi-Fi. No plugging in a USB cable every time you want to tweak the program.
That's huge for industrial settings, I bet.
Absolutely. It's not just convenient, it's a massive time saver, especially if you have lots of these controllers deployed. Imagine crawling around machines with a laptop.
Yeah.
No thanks.
Yeah, point taken. What else?
Second, those essential PLC functions we touched on. Monitor, watch, and force. Got to have those for debugging and testing. We can get into what those mean exactly. Third, it needed to create something called a boot file. So when the ESP32 powers up, it automatically loads and runs the correct control program without intervention.
Right, autonomous operation.
Exactly. And then, specifically for their focus, the agricultural side, ISO-B support was non-negotiable. That's the ISO 11783 standard, particularly the part for HMIs, the screens and tractor cabs, ISO 11783-6.
ISOBIS, okay.
Yeah, which actually led them to make two versions of their solution. One fully open source for general PLC stuff, building automation, that kind of thing, and another open core version that includes the ISOBIS features, because the ISOBIS library they used wasn't open source itself.
Interesting distinction. Okay, let's dive into Eclipse 4diac itself a bit more. You mentioned the IDE, the runtime. How is it structured? What makes that programming part intuitive?
So 4diac, like many industrial tools, has a few main parts. There's the IDE, the integrated development environment. That's where you build your application. Then there's the runtime system, which actually executes that application on the hardware. And there's a library of pre-built function blocks. The IDE will feel pretty familiar if you've ever used Eclipse for anything else. Same kind of menus, symbols, tree views.
Okay, standard Eclipse feel.
Right. But the key part is the graphical programming. It uses something called the ECC Editor Execution Control Chart. Think of it like drawing a state machine or maybe a PetriNet. It's very visual. You define states and transitions. There's also a function block editor, a debugger, and it's actively developed. They mentioned recent stuff like breadcrumb widgets, better search, a problems view, standard helpful IDE features.
And those monitor, watch, and force functions you keep mentioning, how critical are they really?
Oh, they're incredibly important. Monitor and watch let you peek inside the running system. You can see the live values going into and out of your function blocks. You can see status messages like failed to register an observer or whatever. It's your window into what's happening.
Real-time diagnostic.
Exactly. And then force lets you step in and manually override a value during runtime. You just click on an input in the IDE and type in a new value, and the PLC uses that instead of the real sensor input, for example.
Great for testing logic without needing the physical inputs.
Precisely. Super useful for testing specific scenarios or troubleshooting weird behavior. And again, all this happens remotely, over Wi-Fi or Ethernet. It leads to this really neat benefit they highlighted. The model, the nice diagram, directly is executed on the controller.
Meaning?
Meaning you don't draw this nice visual logic and then have to translate it into like messy C code. The visual model is the program. It avoids what they call the ugly code step you sometimes get with things like UML diagrams.
Nice. Seamless development.
Yeah. And the runtime part that makes this possible on the device is called Forte. Forte is the 4diac runtime system. It's designed to be portable, runs on lots of operating systems. Crucially for us, it runs on FreeTOS, which is what the ESP32 uses.
Right.
But it also runs on Linux, Windows, even weird targets like Lego Mindstorm controllers. And it supports various communication protocols like Ethernet PowerLink, OPC UA, and now the ESP32 is a fully supported target within that Forte ecosystem.
Very versatile. So running this powerful Forte runtime on an ESP32, what does the hardware actually need? Can any old ESP32 handle it?
Well, for anything beyond very simple programs, PSRAM is pretty much essential. That's the external RAM chip.
Okay, need that extra memory.
Yeah, the program models can get quite large, so you need a headroom. That means the ESP32 variants that have PSRAM are much better suited. Think ESP32, S2, S3, C3, those types.
Got it. PSRAM is key.
Definitely. Then obviously you need network connectivity. Wi-Fi or Ethernet. Doesn't really matter if it's connecting to an existing network or acting as its own access point. It just needs an IP address for all that remote programming and monitoring.
Right, for the remote access.
And the third piece is a file server running on the ESP32. This is used for uploading a couple of file types, the IOP file, which defines the HMI elements, and the FBT file, the function block pool, and also the crucial boot file, telling it which program to load on startup.
Okay, PSRAM, network file server, makes sense. Now, you mentioned the agricultural market focus in ISOBIS. Did they find existing ESP32 hardware that met those needs, especially the cannabis requirement for ISO, or did they have to build their own stuff?
Yeah, that was a big driver for custom hardware. Finding off-the-shelf ESP32 boards with a canvas, especially rugged ones suitable for agriculture.
Yeah.
Not easy. Most don't have it.
So they had to innovate there, too.
Absolutely. This wasn't just about software. It was about creating the right hardware package. It's kind of the key to unlocking these applications, especially in farming, where isobus and CAN are standard. So they developed several custom boards. The first one they mentioned was called the Huan Moped.
Interesting name.
Yeah, it's a DIN rail mountable unit based on an M5 stack Atom PS. It features 4 smart switch outputs using MOSFETs, not relays.
Why MOSFETs?
Better for higher switching frequencies, and they don't wear out mechanically like relays do. So 4 MOSFET outputs and 3 inputs, a nice compact unit.
Okay.
For bigger needs, they have another DIN rail solution currently going into production. This one's based on the standard ESP32 DevKit C using an S2 or S3 module. That one offers 8 MOSFET outputs, 8 inputs, and importantly, the canvas connector.
Getting more capable.
Definitely. But then they needed stuff for, outside the tractor cab. Waterproof, rugged solutions. So 2 more variants there. One called Dual Out. It's a waterproof box with 2 smart switch output channels, Wi-Fi, and a Canvas.
Okay. Outdoor rated.
Yep. And then for really big systems, there's the Dual CAN module. This one's interesting. 0 outputs on the module itself, but it has 2 CAN controllers.
2. Why?
One connects to the tractor's isobus network. The other runs an internal canvas. This internal bus is designed to connect to other waterproof modules they developed, each having 16 outputs.
Huh. Like an expansion system.
Exactly. You can chain up to 16 of these 16 output modules off the dual CAN controller.
Wow. So that's 16 times 16, 256 potential outputs, plus inputs presumably on those modules too.
Yeah, potentially controlling very large, complex machines. It's designed to be incredibly scalable using that CAN backbone.
That's a seriously flexible hardware setup. Okay, so we have the software framework, the hardware. Let's talk results. What does this actually look like in the real world? Can you give us some concrete examples?
Sure. One really cool one was this open source slurry tanker control. So a farmer in Austria bought a brand new slurry tanker, but without the manufacturer's control system, like bare metal. Bold move. Yeah. And they built a complete control system for it using this Project Logi BUS setup, ESP32 4diac. They paired it with an OX joystick and used a tool called Yeta ISO Designer to create the touchscreen GUI that runs on the tractor's isobus terminal.
So a fully custom open source control for brand new professional equipment.
Exactly. Shows it's not just for tinkering. It's capable of handling real agricultural tasks.
Impressive. What else?
Then there's one they call the retrofit revolution, which sounds pretty transformative and very funny, according to the presenter.
Okay, intrigued. What was that?
They took this really old combine harvester PLC, a Class M easy, think ancient, wires everywhere, tons of connection terminals, just old school.
Right, big clunky box.
Yeah, and the operator's controls were this mechanical box crammed with physical joysticks, switches, buttons. Apparently, it actually blocked the driver's view quite a bit.
Oh dear. Not ideal.
Not at all. So they ripped all that out, replaced it with a full touchscreen system, all running on 4diac and an ESP32, talking isobus to the tractor terminal.
Wow. From that mechanical mess to a touchscreen.
Huge difference. He said it looked much more beautiful, obviously. Functions were color-coded on the screen, much clearer than just knowing switch positions. Driver visibility improved dramatically, and they mapped all the key functions onto a modern, ergonomic joystick.
That sounds like a night and day upgrade. Less clutter, better view, modern controls.
Exactly. Taking something really outdated and making it feel completely modern using this approach.
Yeah.
That's the revolution part, I guess.
You mentioned the presenter called the reaction very funny. Why funny? Was it just the shock of the new?
Yeah, I think it was the contrast. They were just so used to this old, clunky physical interface, seeing it all replaced by a sleek touchscreen. But apparently, once they actually used it, saw the clear layout, the colors, felt the better ergonomics of the joystick, and realized they could actually see better. Any initial surprise quickly turned into appreciation. It just made the job easier and more comfortable, a clear win.
That's great. It really highlights the practical benefits. Okay, let's shift gears slightly and look at a specific programming example. How does this function block approach actually solve a tricky control problem? What was the challenge they showed?
Right. They gave a good example. A customer needed to control a simple on-off output, like a hydraulic valve, maybe using an analog rocker joystick.
Okay, so converting analog movement to digital on-off.
Exactly. But the joystick gives a, say, 0 to 100% signal, And you need to translate that smoothly into output A is on when you push forward, output B is on when you pull back, and both are off in the middle. The tricky part is doing the calculations and managing the thresholds to avoid the outputs flickering or behaving erratically right near the switching points. You need some stability.
Right, you don't want it rapidly switching on-off if the joystick is hovering near the center.
Precisely.
So the solution was this dual hysteresis function block. Sounds technical, but how does it look in 4diac?
That's the beauty of it. It looks quite intuitive graphically. When you see the block in the IDE, the inputs are clearly labeled with descriptions like built-in documentation. Tells you what each connection does. But the core logic is shown in that ECC, the execution control chart.
The state machine diagram.
Yeah, you can literally see the states, neutral, up, down, and you see the lines representing the transitions between them. Those transitions are based on the incoming joystick value hitting certain thresholds, but also incorporating deadbands and hysteresis.
Okay, what do deadband and hysteresis do here?
A deadband creates a small neutral zone around the center point, so slight jitters don't trigger an output. Hysteresis means the threshold for turning on is slightly different from the threshold for turning off.
Ah, so once it's on, you have to move further back towards the center to turn it off, preventing that flickering near the threshold.
Exactly that. It builds in that stability.
Yeah.
And all this logic, the states, the transitions, the hysteresis calculations, it's all represented visually in that diagram. And here's the key part again. That diagram gets loaded directly onto the ESP32. No need to translate it into C or C++ code.
Model-based development in action. What you see is what runs.
Pretty much. It handles quite complex control logic in a very manageable visual way.
Okay, so stepping back then. We've seen the ESP32, this tiny chip, combined with Eclipse 4diac, this open source framework, add in some smart custom hardware, especially for things like Isobis, and suddenly you're democratizing industrial control, right? Making it accessible for farming, maybe building automation, other industrial tasks, going from just a basic software port to controlling real farm equipment, or even, like you said, giving old machines a new lease on life. It's pretty remarkable.
It really is. And it does make you wonder, doesn't it? This mix of open source software, low cost but powerful hardware. How fundamentally might this change things? Who gets to develop and deploy advanced automation now? Could we see like an explosion of innovation coming from smaller companies or maybe in niche areas that couldn't afford the traditional expensive PLC systems before?
That's a really provocative thought to end on. What happens when these powerful tools become so much more accessible? Definitely something for all of you listening to consider. Think about the potential in your own fields, your own projects. There's clearly a lot happening at these intersections of technology. Keep exploring.